start, you remember we were dealing with these, with Lie algebras. You remember what, we took our Lie algebra, we divided into Cartans and roots. There were positive roots and negative roots. Every E alpha had an E alpha, E minus alpha, which was an E alpha dagger. You remember all that. You remember we broke up the space, we looked at some distinguished set of roots called simple roots. These simple roots were the smallest positive roots, okay, in terms of which such that sums of these simple roots made, taking sums of these simple roots, we could get all positive roots. And then their daggers gave all negative roots. You remember that? You remember that we had this sort of key formula, which was that, this key formula, which was that if we took E alpha, E minus alpha, okay, you remember we had this commutation relation, right? Right, first we had Hi on E alpha was equal to alpha I. This was sort of a definition of E alpha. Okay, roots were labeled by their weight, by the eigenvalues under Hi. And you remember we found that E alpha, E minus alpha was equal to 2 alpha dot H by mod square. This you remember? You remember that therefore E alpha, E minus alpha and E alpha, E minus alpha and this guy form the same algebra as J plus, J minus and J3. Okay, and then from that we concluded that if we have any weight, so weight is an eigenvalue under H for any representation vector, that if we have any weight, we concluded that 2 alpha dot lambda divided by mod alpha squared is equal to, let's use the notation we used last time, minus of P minus Q, okay, where P was how many times you had to act with E plus alpha. So suppose you had the weight lambda and you acted with E alpha P times, you got the highest, the SU2 highest weight state. So this guy was J. Okay, and Q was the number of times you had to lower to get to the SU2. So E minus alpha acting with Q acting on lambda give you the SU2 weight minus J. Okay, with these definitions we got this relation. This is, I mean, you have to choose one of the equations that we looked at in the last class that's most important, it's this one. Right, it's the fact that there is an SU2 inside every Lie algebra, and that using SU2 theory we know things about this. Okay, you remember that last class we defined the Cartan matrix, right? We defined the Cartan matrix Aij, which is equal to alpha I dot alpha j divided by 2 mod alpha j square, 2 alpha j square, so 2 mod alpha j, alpha j dot alpha j. Okay, now remember that this matrix was, remember that that these elements were always integers, because in particular alpha is the weight of the adjoint representation, so all those were integers, so are these. Okay, then okay, excellent. Remember also that we argued that for the simple roots, that when we restricted our attention to the simple roots, this matrix was always negative definite. I mean, not definite, negative. Could be either 0 or negative. You remember the argument was that had it been that, you know, we had this funny kind of argument, we take alpha minus something plus something, then it wouldn't be a simple root, that kind of thing. Okay, and these were always integers, they were negative, and we used the Cauchy-Schwarz inequality to show that Aij, Aji was less than or equal to 4. Okay, and we accounted for all the possible values of these Aijs. So -1, -2, -3, or -4, not -4. Yeah, -4. Yeah, -4 was not allowed because you see, if Aij and Aji are related just by this mod alpha square. So if Aij was 0, then Aji was also -1. Yeah, could be, right? And this was strictly not equal if alpha I and was not equal to alpha j. So let's say less than or equal to 3. Why 2? Yes, why not 1 and 3? Yeah, so less than or equal to. Was it? When I is equal to j, that was 4. But 1 and 3 sometimes is allowed, I think. Yeah. Okay, excellent. And now we want to go. We want to go further. Any questions or comments before we continue? Anything you want to remember from the previous class? Okay. And we also had one more definition. We had this definition which was alpha. I think we call it Vi, which is equal to alpha I 2 alpha I divided by mod alpha square. Okay, some rescaled root. Okay, that's often a useful thing. Okay. And we, in terms of this, the condition was that alpha Vi lambda dot lambda. Oh, I sometimes write this with a bracket, was equal to integer. Okay, so now let's continue. Okay, great. There are two things I wanted to say. So, okay, fine. Now, sometimes it's useful to define this thing called the Chevalley basis. Okay, so one basis where you take all basis of what? Basis of generators in your Lie algebra. One basis in your Lie algebra where you take the generators to be these H's and these E alphas and E minus alphas, where alphas are just some highest root, lowest positive root, simple root, and then the more complicated roots as well. This is sometimes called the Cartan-Weil basis. Okay, there's another basis that is sometimes useful. I'll quickly describe it to you. It's called the Chevalley basis. It's a very intuitive basis. Probably some French guy. Chevalley. Okay, so the Chevalley basis, what does it do? Well, it defines Hi. Okay, it defines Hi to be 2 alpha I dot H divided by mod alpha square. Okay, and then the E alphas for the simple. So take the simple roots. Okay, let alpha run over the set of simple roots. Then for any given simple root, associated with any given simple root, it defines this Hi, and then there's E alpha I, which they call E alpha I, and E minus alpha I, maybe I'll call it Ei, just I, yeah, Ei, and E minus I is equal to E. Okay, so this is a linear combination of Cartans, and so is a Cartlan. Okay, this was your simple root, the positive guy, this was the negative guy. Not much of a change, just that in the Cartans, you choose a particular linear combination associated with each root. Okay, Remember, there were as many simple roots as Cartan elements. And so this gives you a basis for, this gives you a basis in the space of Cartans. Okay, so let's write down our commutation relations. Let's write down our commutation relations in this new basis. Sort of, all we're doing is restating that, right? First, of course, let's first do. We had that hi times E alpha was equal to alpha I. Now let's take this and dot it with respect to alpha. So I do alpha I, so that's mod alpha square. I multiply by 2, so I get a 2, and then I divide by mod alpha square. Okay, and so what we and this of course had an E alpha, so this was an E alpha I. Okay, so this guy, this mod alpha square cancels, and we had EIHI. Okay, it's just 2, right? So we get HI. So HI EI is equal to 2 times EI. Okay. Similarly, we get HI E minus I is equal to minus 2 times E minus I. Okay. The nice thing about this basis is that the EI EJ relation becomes simple. So suppose we take EI with the EJ, let's say EI with E minus I. This thing is this thing which was just that, wherever we had written it, it was just 2HI dot EI, E alpha I by mod alpha squared. This is equal to HI. Is alpha I dot mod alpha squared is simply equal to HI by definition. So the relationship that looked sort of complicated in the earlier basis, the relationship that looked complicated looks a bit simpler. It looks EI minus I is equal to HI. Okay? So these relations, of course, make the connection between this and SU2 a little clearer. So far, I've only given you the commutation relations. Okay. So far, I've only given you the commutation relations between EI and E minus I. Okay. Let's now look at what happens when we take E, and of course, if I took EI with EJ, okay, fine, right. So now let's look at what happens when we take HI with what is F? Just I've only looked at what happens when I took HI with EI. But what if I take HI with EJ? Okay? So then what is that? Well, this was simply equal to 2HI dot alpha I by mod alpha I square, commutator with E alpha j. Okay, but that gives us 2, so it's just the charge of E alpha j here, So that gives us 2 alpha j dot alpha I divided by mod alpha I squared times E alpha j. Right? But this guy defines the Cartan matrix Nji. AJI. Right? So I get AJI times E alpha times what we call DI. Okay? So what do we see from this? We see that the weights of I under the Cartan matrix I are just 2. Weights of Lil I under the Cartan matrix Lil HI is just 2. But the weights of EJ under the Cartan matrix HI is given by the Cartan matrix element AJI. This clear? Okay, excellent. Now, that's all very good. That's all very good. The question that is, in order to get the remaining roots of the algebra, what we want to do now is to take, for instance, the various positive roots and commute with each other. Okay? So, the kind of thing that we want to do is, so far we've just looked at what's happening with the simple roots, right? Now, we'll get the rest of the roots of the algebra by taking the commutator of 2 positive, so let's say I want all the positive roots. I take the commutator of 2 positive roots, and I keep going. But of course, this process doesn't go on forever, because this algebra is finite dimensional. So at some point when you do this, you get 0, because now the way of saying it is that our algebra is a highest weight state. Okay? How does that work? Well, we're not going to go through it in this class, but there's this very beautiful relationship. So let me just tell you what it is. It's called the Serre relation. I'm not going to try to go through a derivation unless you guys are very eager, in which case I'll have to work it out and get back to you. Okay? The Serre relation is this. Suppose I define the following. Suppose I define the adjoint action of EI on EJ, let's say, on EJ, to be commutator EI EJ. Let me put I and J up here. Okay? It's the action of EI on EJ in the natural way in the adjoint representation. Okay? Now, so I define this action. So, doing this is the procedure that gives us the higher roots. But we've already said that this thing should terminate at some point. Okay? The question is, when does it terminate? How many times? So suppose I do this adjoint EI-EJ, then I do it once again. I do EI commutator EJ, and just keep going, acting by EI m times in the adjoint representation. Okay? Question, when does this terminate? Okay? So this procedure, EI, then another EI, then another EI, I should put up, sorry, I commutator EJ. Let's say that this is called adjoint EI to the power n. In this case, it will be EI to the power 3. Doing it 3 times. Definition clear? Okay. Now, Serre showed the following. He showed that adjoint EI to the power 1 minus AJI on EJ Yes.
So it is annihilated by E minus I, right? Because you cannot go down, because then again you get Ej minus Ei to be another simple group, which is not possible.
Okay, go on.
Right? So you can only act on Ej by twice the spin of like Ej under Ei, right?
Spin is what? The dot product?
Yeah, the dot product. I mean, these two, Ej transforms under SU2 algebra of Ei, right? And it is highest, lowest speed. You can only make it highest speed by acting with sometimes. And that is like this one.
Let me understand. I hadn't understood this. So let me understand. That sounds interesting. Say again. So Ej is some weight.
Ej has
some weight under the SU2 generated by Ei.
Yeah.
Okay.
And it is lowest because Ej is simple.
It is lowest positive weight.
Lowest positive, right?
Okay.
So if you act on Ej with E minus I.
Okay, so I act with Ej with E minus I. Though this one was Ei. And remember, this guy is always a negative number. So we are always acting with Ei's, E plus I's.
Yeah, that's fine. And,
Yeah.
if you act on Ej with E minus I,
Okay.
it has to be zero.
Why? It's the lowest positive.
Oh, I see. Lowest positive.
Wait.
J was a bigger root than.
Yeah, if J was big.
If J was bigger, then it would be annihilated by E.
Okay, but please keep going.
Yeah, I wanted to say that if it had been the case that it was E minus I, Ej commutator was 0, then we knew that under the SU2 algebra of Ei, E minus I and H, this state was lowest state.
Suppose it was lowest state. Go on.
Yeah, suppose it was lowest state. We know the spin of that state.
Uh-huh.
But by which I mean that.
I see. I now see what you're saying. You're saying that the spin was this basically.
And then we can only.
And then you raise it. You raise it. This is a nice argument. This is a nice argument. And it must be basically what's going on. Okay, let me think about it for half a minute. Let me see if I have anything to say. You're saying that under Hi, this thing had spin this guy, this thing had weight this guy. So it is. Oh, good point. This is I summed over J, summed over I, right? Okay, let's postpone this to later. Yeah, it must be somehow more. I mean, it sounds very nice what you're saying. It must be somehow what's going on. Okay, I will come with a proof next class. It was not summed over. Like, yeah, you're right. It's not summed over. Thanks. It's not summed over. Yes. It's EJ. We just got the same thing with some weight. Yeah. It's correct that it, sorry, thank you. It's correct that it had definite weight. And this must somehow be the key. Okay, it must somehow be the key. But I come next class with a proof if you want. I haven't tried to work this out myself, but it must be somehow the key. It's a good point, I think. It sounds Sounds more or less right. But okay. Okay. Just let's look at what this thing means. Okay. The first thing is that, remember this Aij runs from 0 to -4. Okay? Let's suppose Aij was 0, such that Aj and Ai were orthogonal to each other. Okay? In this case, it tells you that Ei commutator with Ej will just give you 0. Because this works with 1 minus Aij is equal to 1. Okay? The next thing we know, the next thing is that if Aij was 1, then you do the double commutator and you get 0. And you keep going all the way up to 5 times. Okay. You keep going all the way up to 5 times, and this must again somehow be part of it, because we know, sorry, just coming back to your point, we know that if we look at the SU2 representations of the root system, then this cannot become too large. Right? The eigenvalues of this Hi are never more than 4 or -4. Right? So, clearly raising enough times will give you 0. Okay? So, it's not far, but I'll give you a clean proof next. I'll give you a clean proof. It's basically something like this. Okay, excellent. Anyway, so this gives you the structure of the group, because once completely determined in terms of this Cartan matrix. Because I suppose I know this Aij, then I can basically list all the root elements. Because I start with any I, let's say j, and act with Ei some number of times. I might get some of the same elements by starting with j and acting with Ei, or I and acting with Ej. But you know, if you get the same element, you get the same element. Just generate everything you get subject to these rules, and this gives you the whole set of roots in your Lie algebra. So this tells you, this relationship tells you that this. Yeah, the difficulty is in finding out, at least the thing I don't immediately understand is to know which value of P and Q we're at. Because we only know the eigenvalue. We don't know where in the representation we are. Yeah, but something like this. Please.
Can we do it for just Ei, some Ei?
Yeah.
Some power acting on Ei. When j is equal to I, can we have some sense of what's happening when I is equal to j?
When I is equal to j. When I is equal to j, we know the whole representation. Right, so we could just work out anything we wanted to. My suggestion is let us postpone discussion of this point to when we have thought about it. Let's not try to work it out in class. Okay, excellent. What? Yeah, Ei commutator Ei will be 0. That's also true. Yeah, Ei commutator Ei will be 0. That's also true. That will give you absolutely nothing. Yeah. Okay. Excellent. So the importance of the Cheverly basis, one importance is that in this basis, it's very easy to generate the whole set of group generators in terms of this Cartan matrix. Once you know this Cartan matrix, okay, you know everything about these group generators. Okay, so the knowledge of this, so classifying the Cartan matrix is equivalent to classifying the Lie groups. Okay. Now, okay, excellent. Fine. The next thing I wanted to discuss is this notion of fundamental weights. Okay. Weights are just the eigenvalue of any state in a representation under Hi. Okay? But we have seen from that relationship that we had, the PQ thing, that if we take alpha IV times lambda, this thing is always equal to an integer. Okay? So in order, it's nice to do the following. Let's define these weights Wj by the relation alpha iv Wj is equal to delta ij. Okay? So weights, all weights have the property that their dot product with these alpha iv's, with their dot products with alpha iv's are integers. So let's define this dual basis. I've got some alpha iv's. Let's define the basis of weight such that the dot product of omega i, wi, with alpha iv is 1 and with all the others is 0. Had the alpha iv's been orthonormal, these wi's would have just been alpha iv's. But in general, they're not. So it's, that defines these wi's. These, what we have from here is the following, that this gives you, these wi's give you a basis for all allowed weights, an integer basis. So any weight, any allowed weight is some ni wi, where ni's are integers. Okay? So in this basis, all weights are integer weights. Okay? So this basis is the basis of what is called fundamental weights. Okay, okay, great. Now, any irreducible representation has weights that are integer in these fundamental weight basis. And people sometimes define, you see, the fact that you've got these integer combinations of some basis vectors defines a lattice. The set of all possible integer combinations of fundamental weights is a lattice, and all weights belong to the, this is called the weight lattice. All weights are some elements in the weight lattice. Okay? Similarly, by the way, there is this, if you take the set of anything that you can make by sum over mi alpha i's with the simple roots. mi's are arbitrary integers. Okay? That is something. It's not necessarily a root, because roots are of, positive roots are, roots are of this form for specific values of mi's. Okay? But arbitrary linear combinations of simple roots define another lattice. Okay? The second lattice is called the root lattice. Okay? Now, alpha i's are in particular weights of some representation. So, alpha i's can themselves be written as linear combination of the fundamental weights. So, the root lattice is a sublattice of the weight lattice. This clear? It's in very special groups, not SU2, for instance. Okay? In very special groups, the weight lattice is the same as the group lattice. The famous example, root lattice. The famous example of this for string theorists is E8, and this plays a role in determining why it's allowed to be one of the compact, why it feeds into modular invariance of the heterotic string. Okay. Why, by the way, is SU2 is the root lattice different from the weight lattice? Because you see, the weight lattice in SU2 is made up of half integer values of Jz. And these are all allowed weights. However, roots, which are J plus J minus, shift weights by integer values. Okay? So we've got this lattice. It's a very trivial lattice, one-dimensional lattice. With half integer values, that's a weight lattice. We've got a lattice with integer values, that's a root lattice. Okay? And sometimes it is of interest to study one modulo the other. So in this case, the weight lattice modulo the root lattice is just Z2. Okay? So we will come back. Okay, now, why did I say this? You see, within a given representation, you start with the highest weight vector, and you get all the other vectors by acting with alpha minuses. But E alpha minuses. But E alpha minuses are shift your Cartan elements by roots. So, any particular representation needn't lie in the root lattice, but the difference between H's in any particular representation lies within the root lattice. Okay, so if, let's take the case of SU2 for instance. In the case of SU2, if your highest weight was half integer, then all your weights are half integer. On the other hand, if your highest weight was integer, all your weights are integer. Okay, so this all weights within a given representation lie in the same conjugacy class, where if conjugacy class is defined as modding out the weight lattice by the root lattice. Okay, so which conjugacy class you're in is a feature of your representation, not of the stated question. Okay, so representations can be labeled by conjugacy classes, or whatever. I'm not sure conjugacy class is the right idea, whatever, equivalence. Some classes, the classes of which element of root lattice modulo weight lattice you belong to. Clear? Okay, excellent. Now, the next important thing we're going to discuss is what's called Weyl reflections. Okay, let's discuss Weyl reflections. Good.
So, the root lattice is a subgroup of
Sublattice of the weight lattice.
weight lattice.
Yes. Root lattice is a sublattice of the weight lattice.
And then you mod it out.
Any two lattice vectors in the weight lattice that are that differ by a shift within the root lattice, let's define them to be the same. Okay? As we saw in SU2, that gives us two elements.
One for plus one and minus one.
One for integer, the other one for half integer. Okay? In general, for instance, in SUN, there will be n such. There will be n such equivalence classes. There's a nice connection between this and the centers of the group. The center of SUN is Zn.
So there we will get, after modding out, you will get Zn.
After modding out, you will get Zn. It will be labeled by the center elements of the group. We'll come back to this at some point. Okay, good. Other questions or comments? Fantastic. Let's keep going. So we want to discuss these things called Weyl reflections. So let's first start with acting Weyl reflections on roots. We'll also define their action on weights. Okay, suppose I've got some root. Let me stick to his notation. Suppose I've got some root. Let me call it beta. Okay, and now you remember that I've got some other root. Let's call it alpha. Now, associated with the root alpha, there is an SU2. There is an SU2 group. Okay, and beta lies in some representation of that SU2 group. Now, one thing we know about, because we don't exactly know where in the representation it lies. Okay, because we don't know exactly where in the representation it lies, it's not immediately clear from this picture, but we can talk about what the group generated, what the other roots are in the SU2 multiplet of alpha in which beta lies. That was a very complicated sentence, but you understand what I mean, right? It's not, because we don't know how big that representation is yet. However, SU2 groups have the following property, representations have the following property. No matter what representation you belong to, if Jz is an eigenvector, then minus jz is also an eigenvector. Okay? So we know that there must exist another root, okay, which is obtained by acting with alpha lowering operators or raising operators, whatever. Alpha lowering or raising operators, but that takes the jz value from what it was to minus what it was. Okay, so let's put that into an equation. Okay. The difficult thing about this always is to get the factors of 2 right. So let's try. Okay, so we have that we had that E I dot alpha I E minus alpha I was equal to 2 alpha dot H by mod alpha square, and we had identified this with Jz. Okay, we'd identified that with Jz. Great. So now let's find what the value of Jz is. What the value of Jz is for E alpha. Okay, so what we want to do for E alpha j. So clearly the value of Jz for E alpha Ej is just the weights of Ej, so that's equal to alpha I dot alpha j divided by mod alpha I square. That clear? Okay. Now what I want to do is take something which had this this weight. So Jz equals alpha I dot alpha j by mod alpha I square, and add to it some number which I don't yet know, m times alpha I, because I either act m positive m times with the raising operator. Sorry, I add, so let me say it again. I want to take the weight which had weights under all the alpha HIs, which were alpha j, and I want to add to it m times alpha I, right? Because I want to either raise or lower with alpha I m times. M could be positive or negative. And so now I want to look at the j's. I want to choose m so that the jz value of this new vector is minus what I started with, which is minus this. Okay? So I have, I want to choose m. I want to choose m such that the jz value, so that's this. So alpha, I'm supposed to take alpha I dotted with alpha j plus m alpha I divided by alpha I mod square, and I want to make that minus alpha I dot alpha j divided by mod alpha I square. Right, that's what I want to do. Now this alpha I dot alpha I was m. Okay, so we choose m is equal to minus 2 alpha I dot alpha j divided by mod alpha I square. That does the job. Okay, and so we have that the y, what this is called the y, we start with the root alpha j, we apply the Weyl reflection due to the root alpha I. Okay, I started with beta, I called it alpha j. I'm sorry. You understand, right? Was this too confusing? Alpha I. I'm sorry. Let me just redo this with notation alpha and beta. So where I've called alpha as alpha I dot beta I, alpha dot beta minus this was alpha minus beta I minus m alpha. I'm sorry, do you understand? Where I meant to say beta, I said alpha j. You understand? So this is beta minus m alpha dot this, and so on. Right, so this was beta, alpha dot beta by mod alpha square. Clear? Clear? Okay, and so we have that the action of while reflection on alpha j. So the while reflection, let's call it W created by alpha I. Alpha on beta is equal to beta minus 2 alpha dot beta divided by mod alpha square times alpha. Okay, which we can equally well write as equal to beta minus alpha v dot beta times alpha, because our definition of alpha v was this 2 alpha I divided by mod alpha I squared. Okay, so you see that if beta belongs to the root system, this quantity also belongs to the root system. Okay, and this is true for all betas and all alphas. Okay, so the group mapping roots to roots generated by the action of some other root, this reflection of some other root, is sometimes called the while group. Okay, it's sometimes called the while group, and is a very important group in the study of group theory. Okay, now clearly the while group reversed this action on beta, reversed the value of j. So if you act twice, it will re-reverse it. But it's re-reversing it by acting with some number of shifts of alpha, so it will take you back to your original root. Okay? You can check this algebraically. Okay, you can check this algebraically. Put this into the definition of, so act with, okay, the algebraic check would be that if I act with W alpha on this, so W alpha on beta minus alpha V dot beta times alpha, okay, that by definition was the original guy, so that was equal to beta minus alpha V dot beta on alpha, the original guy, minus alpha V dotted with your beta, so that's beta minus alpha V dot beta alpha, okay, times alpha. Okay, and I will leave you guys to check that this thing gives you back beta. This is some algebra you can do. Clearly has to work right. Okay, so if you take any while reflection, I mean this, you take any while reflection by alpha, sometimes people call them S alpha. Clearly S alpha square is equal to 1, more or less by the definition of what this while reflection was. Okay. Now, acting with something that's more interesting, which again I'll leave you to check, is that if you act with two elements, Si and Sj, and I and j correspond to different roots, but such that they are orthogonal to each other, such that their Cartan matrix Aij is equal to 0, then you can, just by manipulating this kind of algebra, you can check that SI-SJ is same as SJ-SI. Okay. So while elements of corresponding, while reflections corresponding to orthogonal roots commute with each other. It's just some algebra like this to check it. Okay? Now, what is the importance of this Weil group? Okay. Actually, before starting that, okay, let me also define the. So far, I've defined. Fine. Okay, let me. What is the importance of the Weil group? The importance of the Weil group is the following. Suppose I do the following. Suppose I start with a set of simple roots and I act with the Weil group on, firstly, clearly the Weil group is a map from roots to roots. Okay, that is clear. Second, if I start with a set of simple roots and I act on these simple roots, okay, if I start with a set of simple roots and I act with these simple roots with these simple roots on any so let me start with, let's say, alpha 1 to alpha r, where r is the rank. This is a collection of simple roots. Okay, and we know that we can produce all other roots. We can produce all other roots by acting with integer combinations of these simple roots. Okay. Now, suppose I take this other collection, which is W alpha 1, W alpha 2, W alpha n. Okay. We can also produce all other roots as a linear combination of these W's. Okay.
Not weights.
Roots. So I'm taking only combinations of roots. Right? So this is all part of, actually just the roots, not even the root lattice.
And these are simple weights.
These alpha 1 to alpha r were simple roots.
No, but this W to WR is constructed from the simple roots, not from the full.
Alpha 1 and alpha to alpha r were simple roots. So now you're acting with W on a collection of simple roots. Now the importance of simple roots was this. We chose some arbitrary ordering system, right? We chose some arbitrary notion of positivity. Within that positivity notion, what was important was that since these were like the smallest guys, okay, these simple roots, that the r smallest roots, it followed that within our notion of positivity, we could construct all the other positive roots as integer linear combinations of these guys. Okay, that followed. Okay, and so what was really important about simple roots was that every other root was some integer linear combination of it. Okay, you didn't need to use halves in that relationship. Now, one can show, and we will see more or less how you show this. One can show that if that property is true for this collection, then it's also true for this collection where W is any Weil reflection. Okay? And therefore, there is some other notion of ordering in which these are the simple roots. Okay? So, you see this arbitrariness that we started with in our discussion of this whole thing. This arbitrariness of what was positive, what was negative. What was small, what was big. We chose some completely arbitrary notion of small and big. Okay? That arbitrariness is reflected in Weil transformations. One notion is related to another such notion via Weil transformations. And as you will see as we build this theory, everything of importance that we will say will be invariant under Weyl reflections. And because of that, everything of importance will be independent of our original choice of ordering of these roots. Okay? Now, let me give you an example of one thing that is independent of Weyl reflections. Let's look at the inner product of two roots. Suppose I take the inner product alpha, alpha. Now let's compare this with the inner product, beta, beta. Okay, let's compare this with the inner product, beta minus alpha v beta, alpha, beta minus alpha v beta, alpha. Okay, so let's just open this out. So this is beta, beta. And now we will have two terms, which is minus 2 alpha v beta, alpha beta. Well, not quite, because there's alpha beta and beta alpha, but okay. Alpha beta, this is all. Anyway, that's right. Alpha beta, beta alpha, basically the same thing. So 2 alpha beta. And then we also have plus alpha v beta, the whole thing squared, alpha squared. Now let's just open out what this alpha v is. So this thing is minus 2, then alpha v itself in its definition had 2, so there was a minus 4. Alpha dot beta divided by mod alpha square, alpha dot beta. And here this had 2 factors of the 2. So that's plus 4 alpha dot beta, the whole thing squared divided by mod alpha squared, alpha squared. Okay, so those cancel and you've got beta, beta. Okay, so in particular we've shown that Weyl reflection does not change the inner product. Sort of obvious, right? We're just changing what we call positive and negative SU2, but anyway, we've shown it algebraically. This kind of algebra you can use to check many of these things. It's not very informative algebra. Okay, excellent, 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 excellent. Now, in the same way that we acted with Weyl reflections on roots, we can also act with Weyl reflection on weights. Because all weights also define some representation of the SU2 generated by alpha. So we can also reflect that weight. Okay, once again the reflection is by acting with some integer number of alphas. In the derivation that we worked out, for what integer it was, we didn't anyway use the property that beta was a root. And so you get the same formula for the action of Weyl reflection on weights. Okay, so S alpha is the camera, do you know? It's there. Okay, so we get S alpha on lambda, this is Weyl reflection by alpha, is equal to lambda minus alpha v inner product lambda. Sometimes I use this thing, sometimes dot, it's the same thing, inner product, minus alpha. Okay, so if you've got a weight associated with any root, we've defined the Weyl reflection of that weight. Okay, now this is a very useful notion in many ways. One way in which it's useful is that it helps you compute, helps you construct the full representation associated with any highest weight. So as we've discussed, or as you know, I can't remember if we've discussed, but representations are labeled by their highest weights. You've got some arbitrary notion of ordering. With that arbitrary notion of ordering, you've got a highest weight in that representation. The importance of that highest weight is that it's killed by all raising operators. All E alphas with alpha positive, with the same notion of positivity. Kill that highest weight. So you can get all the states in your representation by acting with E minus alphas, some strings of E minus alphas on this high weight representation. Now when we're doing SU2, it's very easy, right? There's only one lowering operator, you go down in a line, at some point it annihilates, you're done. But in these general groups, you've got many lowering operators. So you may wonder, what is the full set of weights? What is the full set of weights that we can create starting with the given highest weight? Okay, what is the set of weights that appears inside your representation? Okay, so the answer to that question is given rather simply. Okay. Great. One second. Okay. Okay. Maybe one thing I want to define before explaining this. Just a bit of terminology. Dynkin dy. Okay, so sorry. Before we come to that, there's a little bit of terminology, a little more that I want to describe. Sorry. So let's rewind for that. Yes.
So when you are defining, when you are using this while reflection
Yes.
on your original this root system with
Yes.
some notion of like positivity,
Yes.
or whatever, you will get another such roots, right?
Yes.
But you can have like there is not just two level degeneracy in your argument, right? There can be multiple.
Yeah, you can reflect a root with respect to alpha I, and then reflect that reflection with respect to some other alpha, and so on. That's what you're saying, right? Yeah. The while group is in general a complicated group. In general, it's a complicated group. It's its number of elements in this while group cannot be more than 2 to the power the rank. Right? Because you see, every element is either you reflect, for any element, you reflect or don't reflect with respect to each of these simple roots. Okay? And, is it necessarily simple roots? Just a minute. No. Sorry. 2 to the power maximum is 2 to the power dimension minus Cartan dimension by 2. Because you reflect or don't reflect with respect to any of the roots. Yeah. Okay? But of course, there may be relations between these. Not all of these elements need turn out to be the same. This is the maximum dimensionality of that while group. In particular examples, it will be small.
So it will cover all the different sets of your.
Everything you can do by reflecting in any sets of orders.
And they will be equally valid also.
Yeah, the full group that you get by these reflections, all such reflections, is called the while group. Yeah, so these are generators of any one such reflection is a generator of the while group. Okay, and then you put words of these reflections in any order that you want. Okay, great. Okay, so little more terminology and notation we have to introduce before saying the other things I wanted to say. Okay, first bit of terminology is this thing. Actually, yeah, okay, let's first introduce this terminology and then we do. Okay, so Dynkin labels. the way the numbers, so if you take a weight and you expand it as Ni, Wi, where Wi were the fundamental weights, then these integers Ni are called the Dynkin labels of that weight. Clear? This is just a fancy name for this quantity. Now, if I have an expansion like this, and I want a formula for the Dynkin labels, it's very clear. Clearly, just taking both sides and taking inner product with alpha iv. Because alpha I dot wj was orthogonal. Okay, so this guy gives you a formula for the Dynkin labels associated with any weight. Okay, so not necessarily. You can talk about the Dynkin labels just of a weight. We will often be most interested in the Dynkin labels of a highest weight. Okay, but yeah, that's up to you. Okay, good. Therefore, we conclude that lambda can be written as, this is just some completeness relation. This can be written as alpha iv lambda times w. The sum over I. Okay, and that's true for any weight. Okay. On the other hand, suppose we've got a root. Okay. Suppose we've got a root. Then, let's say beta, okay, can be written as product alpha iv beta times wi, which is sum over I. But alpha iv times beta, let's call this alpha j, beta j, whatever. The jth root, okay. If you don't, okay, alpha j. This thing is more alpha I dot alpha j divided by 2, this is 2 by alpha I square. And so this was equal to nj, or what do we call it, aji. Or was it aij? AJI, I think. The one with the second guy had the thing downstairs. Right? And so we get the following relation. Then any root written in terms of any root can be written in terms of fundamental weights, and the coefficients are basically the elements of the Cartan matrix. So AJI alpha j sum over j. What? Wj. Thank you. Clear? So a root can be expanded in the fundamental basis, and the coefficients of that expansion are this Cartan matrix. Okay. Now we are sometimes interested in doing the following. Okay, we are sometimes interested in doing the following. Did I tell you about this? Anyway, later. We are sometimes interested in doing the following. Suppose I define the following thing. I define Fij, which is sometimes called the quadratic form associated with the group. Okay, this is equal to omega I dot omega j. Okay, so now I can, in terms of this quadratic form, okay, now in terms of this quadratic form, I can do the following. So suppose I have a weight expanded in terms of alpha, alpha IV. So suppose I have I have a weight which is just some suppose I want to expand the fundamental weight omega I in terms of these alpha IVs. For whatever reason, suppose I want to do it. So I want to write this as zeta j alpha jv, sum implied. Okay, if I wanted to do it, then I can easily find this coefficient just by taking dot product with omega j on both sides. Wj. This gives you Fij. These are symmetric things. So I get Fij is equal to zeta j because of the orthogonality. And therefore, we find the following relationship. We find the relationship omega I, so omega I is equal to Fij alpha jv. Okay. Omega I is Fij alpha jv. But we also learn from here that alpha I for any root was equal to Aj omega j. Right? So I can take this relation and just multiply by 2 mod alpha I squared on both sides. I was just a free index here, so I could just do that. Okay? And then this is just alpha IV. And you notice that these two relations are inverses of each other. Oh, so we see that F inverse is equal to, F inverse Ij or Ji is equal to 2A by alpha squared. You have to keep your wits about you to see which is I and which is J, but up to that it's clear, right? Right? So this matrix of inner products, this thing that we call the quadratic form, is basically the inverse of the Cartan matrix, or more precisely, the inverse of the matrix of this quadratic form is basically the Cartan matrix up to this renormalization of one of its legs. Okay? Excellent. Excellent, excellent, excellent. Okay, one last thing before we move. Is there? Okay, clear. One last thing we want to discuss. Oh, two last things if you want to discuss. You guys have a little time. We can go until 4:15. Yeah. Two last things we want to discuss on this. Okay. Associated with any representation, well, there is this thing that when we discuss SU2, an important thing in the discussion of SU2 was the Cartan of SU2, like was the Casimir of SU2, this thing that evaluates to j into j plus 1. Okay? For any group, for any such group, there is a Casimir. The Casimir in basis in which we've normalized all our generators such that JA dot JA is 1 is just JA sum over A. Okay? And this thing is invariant basically because the action of group rotations on the adjoint is a real unitary representation in terms of a real basis. Okay, but we had normalized our E alphas not to be 1, but we had chosen the normalization E alpha, E minus alpha E alpha E minus alpha was equal to, what was it, 2 by mod alpha square. Okay? So if we rewrite this JA, sum over A, JA, in terms of the H's, which were usually standardly normalized, and these E alphas, we're going to get an extra factor of mod alpha squared by 2. And so the Casimir, the quadratic Casimir, the thing that commutes with the action of generators, is sum over I hi squared plus sum over I E alpha E alpha I E alpha minus I. Now maybe this requires E alpha minus I, alpha, let's call it EI, E minus I, plus E minus I, EI, the whole into mod alpha squared by 2. That's to undo that normalization. Okay, this is an object that commutes with the action of the group, and so is constant on a representation, just like J into J plus 1 for SU2. Okay? Now this object, when we study current algebras, we will need, there are many things that are determined in terms of Casimir of representation and so on. So we will need to be able to calculate Casimirs of representations. Okay? And there's a very easy way to calculate the Casimir of a representation, just mimicking what we do with SU2. Since the Casimir, let's suppose we've got a representation whose highest weight is lambda. Some weight lambda. Okay? Now, what we're going to do is to just act with this Casimir operator on lambda. We expect to produce something times lambda. And once we can identify that number, that will be the Casimir, the value of the Casimir on any state in that representation. Okay, so let's go ahead and do that. See, it's easier than you think. Firstly, this hi squared is just lambda I squared. So this part just evaluates to lambda I squared. Okay. What about these guys? Since this is highest weight, action of the raising operator on this guy just kills it.
Sorry, are these simple? These are not simple, right?
These are any roots, but let's say that we've taken them to be all positive roots. Okay, so i's, that's why we've got I and minus I. Okay, so any positive action of any positive root kills it. Okay, on the other hand, the action of the negative roots don't kill it. The action of the negative roots don't kill it, but we get this on lambda. So what I'm doing is writing Q on lambda. We get this on lambda plus mod alpha I squared by 2 EI E minus I acting on lambda. Okay. Now we know that EI, E minus I acting on lambda has the same weight as lambda, because EI and E minus I together have zero weight. So once again it's proportional to lambda, so it's some number acting on lambda. Question is what number? Okay, but that's not hard to not hard to find. What we do is the following. We just take the inner product of this with lambda. Okay, so we'll write this as sum over I mod alpha I squared by 2 lambda EI E minus I lambda. I'm just interested in the number. So I'm taking inner product, I'm assuming lambda as unit normalized.
You can just take commutator and that will give you
Exactly. Exactly. Okay, that's what I was going to do at this step. Okay, so I take EI, E minus I, and then I take this guy through. Yeah, I could have done it without taking the inner product. It's true. I could have done it without taking the inner product. It's true. I take this guy through, and I get, so then when I take this guy through, that kills it. So all that remains is the commutator, and the commutator was equal to 2 alpha I dot H divided by mod alpha I square. Okay, and so this gives you 2 alpha I dot lambda divided by mod alpha square. And so the final result for the final result is that the action of Q, okay, the action of Q is equal to lambda I squared, sum over I, plus sum over all positive roots, so all root and anti-root systems, I times mod alpha. This mod alpha I squared by 2 is cancelling this 2 is cancelling this, sorry, mod alpha I square by 2 is cancelling this 2 is cancelling this. So I get alpha I dot lambda, where this sum is taken over all positive roots. Okay, so we've got this very simple expression for the quadratic Casimir, a very simple expression for the quadratic Casimir of any representation, which is easy to apply. Now it can it's written, okay. Now this sum over I, sum over alpha I appears in overall positive roots, appears in many different formulae. So it's good to give it a name. In fact, the standard definition is sum over alpha I by 2. So let's define rho is sum over all alpha, all positive. Okay, this by 2. This object rho is sometimes called the Weyl vector. Okay, so in terms of the Weyl vector, Q is written as inner product of lambda with lambda plus 2 rho. Right, because sum over alpha I is 2 rho. So this is a famous formula for the quadratic Casimir of any representation, derived, of course, as you see, extremely simply.
This is true for the simple root, lambda being the simple root.
No, lambda is the highest weight vector.
Yeah, highest weight.
Highest weight vector of the representation.
Yeah, but this should be true for any state in that representation.
The answer is true. For any state in the representation, Q acting on that state is this where lambda is the highest weight. It's like j into j plus 1. In fact, if you apply this to SU2, j into j plus 1 is j squared plus j. Okay, the j squared is that sum over lambda I squared. That's the j squared, and the j is the lambda dot alpha. Okay, so there, of course, as you know, every state in the representation has Casimir j into j plus 1, but where j is the weight of the highest weight state.
Yeah. So what I was asking is if Q if you do Q acting on some E minus alpha acting on lambda.
Yes.
It should give you the same.
It gives you the same answer, but won't give you weight of that. You know, it won't be that this formula is true where lambda is replaced by the weight of that state.
Yes.
It
should be the highest weight.
It's the weight of this high state. Yes. It commutes with E alphas. This a quadratic Casimir. Okay, clear? Okay, we should soon stop. Just one more thing. I'll just describe one more thing. Okay, excellent. Okay, maybe I'll just stop with this. I don't know if you remember, but last class, I forgot to tell you about it in our review. We gave a special name to the highest weight state for the root lattice, for the adjoint representation. We called it theta. It was the highest root. Okay, that object. So there's rho, which is this Weyl vector. That's some famous thing. Theta, which is the highest root, is also will appear many times. So let's, as an application, let us work out the value of the quadratic Casimir for the adjoint representation. Okay, so the quadratic Casimir for the adjoint representation is just this, but with lambda replaced by theta, because it's the highest weight vector for the root system. So we've got theta plus 2 rho. Okay. Now, okay. It is okay. Let's work it entirely in terms of is mod theta square. Okay, mod theta square plus mod theta squared plus 2 theta rho. Okay. No. Oh, and I've not discussed this. Okay, so this maybe we have to. Okay, I'll just tell you what I was planning to tell you, but it uses an identity whose derivation I've not yet discussed, so we will. Just the first thing we will do in the next class is to prove the following. We'll prove that rho, which is sum over all positive roots by 2, is also given by what is this formula? Is also given by sum over I wi, sum over all the fundamental weights. Okay, this will be unsatisfying. Let's postpone this. Let's postpone this to next class. So I wanted to show you the relationship between the quadratic Casimir acting on the adjoint representation and the dual Coxeter number. But in order to do that, I have to show you that this is also the case. So it's 4:20. Let's not try that this class. Next class, we will start next class by doing this derivation. Okay, let's stop here. Okay, I'm sorry this is going on forever. If you guys are feeling really bored, I think we'll need one more class on Lie algebras. I wanted to talk about characters, the Weyl character formula. I wanted to talk about branching rules and things like that. How many of you people know all of this? Am I boring everyone here? No? Okay, so we will continue next class. One more lecture on the algebra. What? Racah-Spice algorithm. Okay, we can discuss the Racah-Spice algorithm. Yes. Great. Okay, we can do that. So we have one more class on Lie algebras before we move on to affine Lie algebras. I think that one class should do it. I wanted to discuss Weyl character formula, branching rules, maybe Racah-Spice algorithm, maybe some Young tableau methods. Okay. Dynkin diagrams. We've not even introduced Dynkin diagrams. Right? I will go through this discussion of Dynkin diagrams. Maybe one more lecture should do that. And then we will move on to the